Hello everyone. Now this is the lecture 4 of unit 5, that is Nano Materials. So we have started this Nano Materials, and now I will repeat the introduction to the nanotechnology again, right? So the content that we'll cover in this lecture are introduction to nanotechnology. Then we'll see some special topics in nanotechnology, that are molecular machines, beyond nanotubes, nanowires, and applications of nanomaterials in electrical engineering. So in lecture 3 we have already covered some special topics in nanotechnology, that is the single electron transistor and quantum dot, right? That is the building block of the single electron transistor. So the introduction to the nanotechnology. So nano is what? Nano is 1 billionth or 1000 million, that is 10 raised to minus 9. So 10, then nanometer, it's 10 to the minus 9 meters. So here is 100,000 nanometers thick. So that is 1 billionth of a meter. Nanoparticle is a 1 millionth of a millimeter, and that is a size dependent property, that is the nanoparticle. Nanocrystal is a material particle having at least one dimension smaller than 100 nanometers and composed of atoms in either a single or polycrystalline arrangement. Nanoalloy. So nanoalloy is an alloy consisting of dispersed nanoparticles of 2 or more metals. Nano engineering is the practice of engineering on the nanoscale. It derives its name from the nanometer, a unit of measurement equaling 1 billionth of a nanometer, and that is the nano engineering. Then nanostructure is a structure of intermediate size between microscopic and molecular structures. So the nanostructural detail is microstructure at nanoscale. Nanodot, and that is similar to the quantum dot, can refer to several technologies which use nanometer scale localized structures. Nanodots generally exploit properties of quantum dots to localize magnetic or electrical fields at very small scales. So the applications of nanodots could include high density information storage, energy storage, and light emitting devices. Nanomedicine is the medical application of nanotechnology. Nanomedicine ranges from the medical applications of nanomaterials and biological devices to nanoelectronic biosensors and even possible future applications of molecular nanotechnology such as biological machines. Current problems for nanomedicine involve understanding the issues related to toxicity and environmental impact of nanoscale materials. So the materials whose structure is on the scale of nanometers, that is the nanoscale materials, that is 1 billionth of a meter. Frozen organs could be brought back to life safely one day with the aid of nanotechnology. With improved tissue cryopreservation using inductive heating of magnetic nanoparticles. So now we'll start the special topics in nanotechnology, and that is the molecular machines, right? So what is a molecular machine? So it is a nano machine, right? Or we can say that tiny energy conversion devices on the molecular size scale, whether naturally occurring or synthetic. These machines are generally more efficient than their macro scale counterparts. So they have their own mechanochemistry, dynamics, workspace, and usability, and are composed of nature's building blocks, namely proteins, DNA, and other compounds built atom by atom. So with modern scientific capabilities, it has become possible to create synthetic molecular devices and interface them with each other. So countless such machines exist in nature, and it is possible to build artificial ones by mimicking nature, right? So molecular machines are the nano machines, and that is possible in any discrete number of molecular components that produce quasi-mechanical movements, that is output, in response to specific stimuli, that is input. So the expression is often more generally applied to molecules that simply mimic functions that occur at the macroscopic level. So the term is also common in nanotechnology, where a number of highly complex molecular machines have been proposed that are aimed at the goal of constructing a molecular assembler. So the molecular machines can be divided into two broad categories, that is synthetic and biological. So the molecular machines can be defined as devices that can produce useful work through the interaction of individual molecules at the molecular scale of length. So what is the unit of that length? The convenient unit of measurement at the molecular scale would be a nanometer. Hence, molecular machines also fall into the category of nano machines. Molecular machines depend on inter and intramolecular interactions for their function. These interactions include forces such as the ionic and van der Waals forces and are a function of the geometry of the individual molecules. Now classification. A majority of natural molecular machines are protein based, whereas the DNA based molecular machines are mostly synthetic. Nature deploys proteins to perform various cellular tasks, from moving cargo to catalyzing reactions, whereas DNA has been retained as an information carrier. We know that. Hence, it is understandable that most of the natural machinery is built from proteins. With the powerful crystallographic techniques now available, protein structures are clearer than ever. The ever-increasing computing power makes it possible to dynamically model protein folding processes and predict the conformations and structure of lesser-known proteins. Hence, the molecular machines are divided into three broad categories, and that are protein-based, DNA-based, and chemical molecular motors. Now, construction. So as we have seen that there are three categories of molecular machines: protein based, DNA based, and chemical based, right? So first we'll see the protein molecular machine, that is adenosine triphosphate based ATP based protein molecular machines. So in this machine, the protein based molecular motors rely on an energy rich molecule known as adenosine triphosphate, that is ATP, which is basically a nucleotide having three phosphate molecules that play a vital role in its energetics and make it an indispensable commodity of life. The machines of protein molecular machines depend directly or indirectly on adenosine triphosphate for their input energy, that is stimuli. So the F1 motor, powered by hydrolysis of adenosine triphosphate ATP, is composed of a central protein stalk called the Y, that is gamma subunit, surrounded by three copies each of alpha and beta subunits. The alpha and beta subunits are arranged alternatively so that they make a symmetric circular pattern when viewed from the top. So it is shown in figure. So there are delta subunits attached to the periphery of the alpha beta cylinder, and the sigma subunits are present at the base of the gamma subunits as shown in figure. Right, so here you can see that there are alpha, beta, and gamma subunits, and that are based on the uh, sigma subunits, right? And there are also delta subunits attached to the periphery, right? So it is shown in figure. So here is the F1 motor that we have seen, that is ATP based protein molecular machine, is composed of 9 polypeptides. The alpha and the beta subunits contains nucleotide binding sites that bind ATP, that is what? Adenosine triphosphate, and ADP means adenosine diphosphate molecules. So the nucleotide binding sites in the alpha subunit simply bind the nucleotide, whereas E those whereas those in the beta subunit actually perform the catalysis. So the A, B and the C subunit shown in figure 1 are a part of the F0 motor, right? That is discussed above, right? Now we'll see some other motors. That is second one is what? DNA based molecular motors. So as we have discussed for the protein based molecular motor, similarly in the DNA based molecular machine, DNA mainly acts as an information carrier, right? There was no mechanical work assigned to it. So energy conversion, trafficking and sensing were the tasks assigned mainly to proteins, right? So probably for this reason DNA turns out to a simpler structure with only 4 kinds of nucleotide bases, that is adenosine, thymine, guanine and cytosine. That is A stands for adenosine, T stands for thymine, guanine is G and cytosine is C, attached in a linear fashion that takes a double helical conformation when paired with complementary strand. So such structural simplicity in proteins made of some 20 amino acids with complex folding patterns results in a simpler structure and predictable behavior. So there are certain qualities that make DNA an attractive choice for the construction of artificial nanomachines. Right? So in recent years, DNA has found use not only in mechanochemical but also in nanoelectronic systems. So a DNA double helical molecule is about 2 nanometer in diameter and has 3.4 to 3.6 nanometer helical pitch no matter what its base composition is. So structural uniformity not achievable in this, right? With protein structure if one changes their sequence, right? So this is the DNA molecular machine. Now the third one is what? That is inorganic or chemical molecular machines. As we have seen that in the past 2 decades, chemists have been able to create, modify, and control numerous types of molecular machines. So many of these machines carry striking resemblance to our everyday microscale machines such as gears, propellers, shuttles. Right. So in addition, all of these molecular machines are easy to synthesize artificially and are generally more robust than natural molecular machines. So most of these machines are organic compounds of carbon, nitrogen and hydrogen. So with the presence of a metal ion being required occasionally, electrostatic interactions and covalent and hydrogen bonding play essential roles in the performance of these machines. So such artificial chemical machines can be controlled in various ways: chemically, electrochemically and photochemically. Through it. Photochemically means what? Through irradiation by light. Right? So instead of this, all these are what? The different types of molecular machines. Now how these molecular machines works? So working principle. Molecular machines depend on inter and intramolecular interactions for their function, that we already discussed. So these interactions include which forces? Ionic and van der Waals forces, and these are the function of the geometry of the individual molecules. So the interaction between two given molecules can be well understood by a set of laws governing them. So which brings in a definite level of predictability and controllability of the underlying mechanics. So Mother Nature has her own set of molecular machines that have been working for centuries and have become optimized for performance and design over the ages, right? So the binding change mechanism to explain the function of the protein-based molecular machine was proposed in 1973, and that mechanism is known today. Shows that each of the beta subunits take three forms: O, L, and T. O, open, L stands for loose, and T stands for tight. So take three forms: open, loose, and tight binding site, right? So the mechanism that we know today, that is known to us today, is the what? That each of the beta subunits take three forms: open, loose, and tight binding site. So when the subunit is in the form of open, it is catalytically inactive and has very low affinity to bind substrates. Now in the L form, means in the loose form, the subunit loosely binds substrates, that is adenosine phosphate and phosphate ion. So although it is catalytically inactive, right? Now in the tight form, the adenosine phosphate and phosphate ion are converted into a tightly bound adenosine triphosphate until a conformational change converts the tight site into an open site, thereby allowing the release of the newly formed adenosine triphosphate. So the mechanism is shown below it. So that is the binding change mechanism of adenosine triphosphate based molecular machine. The recent explosion of research in nanotechnology combined with important discoveries in molecular biology has created a new interest in biomolecular machines and robots. The main goal in the field of biomolecular machines is to use various biological elements whose function at the cellular level creates a motion, force, or a signal as machine components that perform the same function in response to the same biological stimuli. That is what? Input, but in an artificial setting, right? So in this way, proteins and DNA could act as motors, mechanical joints, transmission elements, or sensors. So here the molecular machine mechanism is related to our natural body mechanism, right? So the future of molecular machinery is bright. We are at the dawn of a new era in which many disciplines will merge, including robotics, mechanical, chemical, biomedical engineering, chemistry, biology, physics, and mathematics, so that fully functional systems will be developed. However, challenges toward such as goal abound, right? So developing a complete database of different biomolecular machine components and the ability to interface or assemble different machine components are some of the challenges to be faced in the near future. So every innovation or research have some challenges, right? So the problems involved in the controlling and coordinating several biomolecular machines will come next. So when we have a overall knowledge of the molecular machine, then we can have some applications. So the ever increasing computing power makes it possible to dynamically model protein folding processes and predict the conformations and structure of lesser known proteins. So this is one application. Then these findings help unravel the mysteries associated with the molecular machinery and pave the way for the production and application of these miniature machines in various fields including medicine, space exploration, electronics, and military. Outstanding and exceptional physical properties of material can emerge when its size reduces to the nanoscale. Developing nanostructure processing developing nanostructure possessing unique feature has always been the essence of nanoscience and nanotechnology since the beginning. So among various nanostructures in general and all kinds of one-dimensional network in particular, nanotubes have built a strong reputation as the most widely studied nanomaterial. So take an example of carbon nanotube. So theoretical and experimental research in every aspect of tubular nanostructure have been flourishing ever since the first discovery of carbon nanotube in the early 1990s. The carbon nanotubes offer numerous fascinating applications in electronic, sensing, composite, and many more are being progressed. So the development of new class of nanotube besides the famous carbon allotrope has become an attractive topic in recent years. Right now we'll see the second special topic in nanotechnology, and that is the boron nitride nanotubes. So what are these BN nanotubes? That are boron nitride nanotubes, and are similar to the tubular structure as carbon nanotubes, in which carbon atoms are replaced entirely by boron and nitrogen atoms arranging in a hexagonal lattice as shown in figure. Right, so figure 1 indicates that the carbon nanotube, and B that the hexagonal arrangement is replaced by boron and nitrogen atoms, and that is the boron nitride nanotube. So because of its similarity, both BNNT means boron nitride nanotube and carbon nanotube share some identical intrinsic characteristics, and that are excellent mechanical properties, high thermal conductivity. Now the synthesis methods. The essential factor rendering efficient boron nitride nanotube synthesis process is the rate of conversion from boron and nitrogen sources into boron nitride radicals, that is BN radicals. So each fabrication technique was scientifically developed in different and distinct strategies involving specific precursors, conditions, and equipment to promote the growth of boron nitride nanotube. So the fabrication techniques are arc discharge, chemical vapor deposition, and laser ablation. Right. So first we will see the arc discharge method. Now in 1995 it was first seen that BN boron nitride nanotube was accidentally found in arc discharge, and that is in 1995. In that case, a boron nitride rod as a precursor for nanotube synthesis was inserted into a hollow tungsten anode electrode. Arc plasma generated between the anode and cathode quickly vaporized the anode part. Right? So the synthesized boron nitride nanotubes had an inner diameter of 1 to 3 nanometer and a length of 200 nanometer, and one end wrapping a dense particle, probably tungsten or tungsten compound with boron and nitrogen. Because of the insulating property of boron nitride rod that can hamper discharge process, it was later replaced by highly conductive boron containing chemical compounds or a mixture of boron and nickel, cobalt and nitrogen was used as surrounding gas. So by doing so, it not only increased the conductivity of anode but also provided catalytic activity toward nanotube growth. Right? So in this case, the main disadvantage of arc discharge is that it is hard to produce boron nitride nanotube at large scale, as the reaction zone at the arc core is confined in a small volume, right? Now the second fabrication technique is chemical vapor deposition. Chemical vapor deposition is one of the most popular way that have been widely used to produce carbon nanomaterials, and it was lately adopted to synthesize boron nitride materials. So in comparison to other approaches, this technique offers better controllability of growth parameters regarding growth mechanism, experimentally set up precursors, catalyst, and temperature. So to ensure the high quality of nanomaterials, right? So it is not surprising that uh, Chemical vapor deposition process for boron nitride nanotube growth is relatively similar and reminiscent of carbon nanotube synthesis. The difference lies primarily in the types of starting materials, growth conditions, liquid and solid boron and boron nitride sources, right? So the boron and boron nitride sources are commonly used to grow boron nitride nanotube instead of toxic and combustible gases. Boron precursors along with nitrogen gases such as nitrogen and ammonia, also similar to carbon nanotube synthesis. Transition metal catalysts are particularly efficient at producing BN and T with few layers and small diameter, right? So here in chemical vapor deposition that we have seen that liquid or solid boron and boron nitride sources are commonly used for the growth of BNNT instead of toxic and combustible gases, right? So instead of toxic and combustible gases, boron precursors along with nitrogen gases are used, right? And it is similar to what carbon nanotube synthesis. That is, in that case, transition metal catalysts are particularly efficient at producing BNNT with few layers and small diameter, right? So the chemical vapor deposition process for boron nitride nanotube growth is similar and reminiscent to the synthesis process of carbon nanotube, right? So now the third method is what? Laser ablation, right? So in this laser ablation method, the fabrication of boron nitride nanotube has the advantages of producing high quality nanotubes with small number of the wall, then high aspect ratio and crystallinity, right? So what are the advantages of laser ablation method for the fabrication of boron nitride nanotube are that high quality nanotubes production is possible with a small number of wall, high aspect ratio and crystallinity, right? Okay, so in this method a target made of boron or boron nitride undergoes a phase transformation from solid to liquid at a high temperature that exceeds boron melting point up to 2000 degrees centigrade due to laser heating. So thus direct reaction between surrounding nitrogen atmosphere and boron target can be enhanced efficiently, resulting in the efficient growth of boron nitride nanotubes, right? So the multi-walled boron nitride nanotubes were synthesized by laser heating cubic and hexagonal BN targets, right? So until 5000 Kelvin, right? So in a diamond anvil cell is extremely high pressure of nitrogen gas. Okay, so this is what laser ablation method. So in laser ablation method, that the heating process is developed, and that is up to 2000 degrees centigrade, where the boron melting processes happened. Now the applications. So based on various unique properties, boron nitride nanotubes have great potential for practical uses in many areas. Despite limitations on fabrication technique, there is an increasing number of fundamental studies suggesting and developing boron nitride nanotube applications. So significant successes have been achieved, and in most cases, boron nitride nanotube is conclusively proved to be a promising candidate for mechanical reinforcement in the nanocomposite and advanced functional materials. Now the third special topic in nanotechnology is nanowires. So nanowires have two quantum confined dimensions and one unconfined dimension. Therefore, the electrical conduction behavior of nanowire is different from that of their bulk counterpart. In nanowires, electronic conduction takes place both by bulk conduction and through tunneling mechanism. So the high density of electronic state, diameter dependent band gap, enhanced surface scattering of electrons and phonons, increased excitation binding energy high surface to volume ratio and large aspect ratio, nanowires of metals and semiconductor exhibit unique electrical, magnetic, optical, thermoelectric and chemical properties compared to their bulk parent counterparts. So based on these properties, there are some applications of nanowires, and that are magnetic information storage. Then nanowires are used to fabricate stable magnetic medium with packing density of 1011 wires per centimeter square. Then for thermoelectric cooling system and energy conversion devices, and nanowires are also used in numerous electronic applications. Now the last content of this lecture is applications of nanomaterials in electrical engineering. So by reviewing the whole lecture, so it is clear that the nanomaterials are used in lasers, then in batteries. In batteries, in 2005, Toshiba launched a rechargeable lithium-ion battery which used nanoparticles. Now, and in fuel cells and photovoltaic cells. In electric double layer capacitors as a hybrid energy source for electric vehicles and portable electric devices. In lead-free solder, now in this case the company Motorola is leading a low temperature lead-free nano solder initiative. Right? So the silver nanoparticles as coatings are also used in Samsung washing machine. So Samsung have developed techniques for using them in the wash cycle, the so-called silver wash. That is silver wash technology, which is designed to improve the washing of clothes. Right. So thank you all.